So in this video we're going to be going over how to make a symmetric cell with lithium metal electrodes and LiPF6 electrolyte. So once we build this cell, then we're also going to create a job file to simulate the cell. And in this simulation we're going to be plotting the mass transfer of the two electrodes as a function of time, the lithium concentration and electrolyte potential, and the EIS. So in this cell we see that in this diagram we see the cell, and based off the direction of the current we see that the lithium ion plus is going to be moving from the right to the left. So it's going to be leaving the right plate and depositing onto the left plate. And then below that are the constants or parameters that we'll be using for the materials. And to the right of that are the mathematical equations that govern this entire process.
This video is going to be a basic simulation setup for electrochemical devices using RandFlux. So first, what we're going to do is we're going to start a new file, open an electrochemical device, and then next we're going to add a region. And in that region we're going to just define the type of structure it is, and it's going to be an electrolyte only structure. Next we'll add in what type of electrolyte it's going to be using, and it's going to be LiPF6. And then the next thing we're going to be doing is that we're going to add a reaction for the anode and electrode. So first we're going to go and right click on the chemical reactions, add reaction, and RandFlux will already show us what type of reaction we'll be using, or it'll auto suggest. And then next we're going to go with the Butler-Volmer kinetics full equation. Next thing we need to do is we do this very same thing on the cathode side, and then reaction, Butler-Volmer kinetics, and then next what we're going to be doing is we're going to have initial conditions. So in this case we're going to go over here and we're going to give the initial conditions of 1e negative 4. And the same over here, 1e negative 4. And then next we're also going to need to define the initial conditions on the electrolyte. So we're going to be putting down 1000 for the lithium ion, and then same for the PF6 minus. And then next we're going to simulate the device. But first we need to save this. So we're going to save device. We're going to name it after cell 1. So next we're going to simulate the device. We're going to like change the window. Alright. So next, before we do that, we need to know how the whole setup, or how the circuit setup is going to look on RandFlux. So what we're going to do is we're going to show information about the circuit. So in this case, what we're going to have is that we're going to have the cathode being the only thing that's available in this circuit. So we're going to have to cut off this portion over here on the anode side, and we're also going to make sure that there's nothing coming from the cathode side for the voltage portion. So in this, we're going to have to set the variables. We can also check mark the anode and cathode currents, and also change the value of the cathode to be 1 milliamp, or in this case 1e negative 3. Next, we're also going to need to change the values of the resistance. We also need to enable them first, and we're going to be changing the resistance of the anode to be 0. So then, okay this. And another thing that we need to do is we need to remove the compute bias point, since we will not be needing this, and instead we'll be adding a sweep variable. Oh, just so you know, you can either use the hotkeys for this for control up and control down to move the positions of where the jobs are. So as RandFlux sees these as the first step, second step, and then the third step. So next, what we're going to be doing is we're going to be showing what variable is going to be swept. So in this case, we're going to be sweeping this over time, and we're going to be sweeping this from to 3600 with the initial step, with the minimum step of the initial step of 60 seconds, or in this case 1 minute. The 3600 is to represent the 1 hour, and then the maximum step is going to be 600, or in this case 10 minutes. Next, we're also going to be plot 2D. We're going to name this electrode mass, and then the curve name is going to be the which electrode is going to be. So in this case, it's going to be the anode. X-axis is going to be time, and then the y-axis, we'll need to look for the proper variable. So in this case, we're going to be using the mass of the anode, which will be this here, but we can't leave it as is because it only gives us in moles. So we need to multiply this by the molar mass of lithium, which will be 6.94. Next, we do the same, but for a cathode. Electrode mass, cathode. Press OK. Now we're gonna save. Oh wait, before we do that, we also need to save this. We're just going to name this cell 1 as well to go along with this. Next, we're going to run this just to see how it will look for the output. And as you can see, that the mass of there's a mass transfer between the two electrodes. So next, we're going to get rid of these. And now we also want to plot the concentration of the lithium after 3600 seconds or 1 hour has passed. So next, we're going to go here, and we're going to plot in a new window, finite element devices. And in this, we're going to get the concentration. And next, we're going to plot this as well. So here we see the concentration of the lithium going down as it goes from 0 to 100 micrometers, and this is after 1 hour.
So in this section, we're going to be going over the EIS and RandFlux. So the one thing that we want to do is that we want to create a custom variable, and we're going to name that f, and this f is going to be representative of frequency. Next thing we want to do is that we want to create a set variable, and we're going to set this value of f to be 1e minus 3. Press OK. And then the next thing we want to do is that we want to do a small signal analysis. So what we're going to be varying harmonically, or the signal that's going to be varied, is going to be the I cathode current. This is going to be normalized to 1, and we're going to have the frequency being varied be f. And the parameter that we're going to be analyzing is going to be z. This is going to be our frequency. So we're going to just name this z, and then we're going to be using my device cathode potential. Press OK. In this, that's the reason as to why we're using the cathode potential, since we normalize the current to be 1, and since Z is equal to V over I, Z is going to be equal to V in this case. The next thing we want to do is that we want to set it up so that frequency is varied with each iteration. So we're going to do 1.1 times F. And the next thing we want to do is that we also want to create a plot for this. So we're going to do 7 variables to plot pain. And in this we're going to name the pain name EIS, and the curve name is going to be named impedance. And for the x-axis we're going to use the real values of the impedance. And for the y-axis we're going to use the imaginary values of the impedance. Press OK. And then the last thing we need to do is that we need to also set up the for loop. And so in this case we're going to use the repeat tool, or the repeat job. We're going to have it repeat the previous 3 jobs, and we're going to have it do it 100 times. And with all that set, then we run this. And with that, there is our impedance curve.